this video, I'll be discussing about continuity and infinite limits. Let's head to continuity first. When we talk about continuity, or when we refer to a certain function that is continuous, we always mean that this graph, let's say f of x, has no interruptions. And when we say interruptions, we are referring to any kind of discontinuity, may it be holes, gaps, or jumps. In this case, I have a function f of x. I also have g of x, which is in the green color, h of x in the orange color, and j of x, which is yellow. Among these functions, you could say that f of x is a continuous function simply because it doesn't have holes, gaps, nor jumps. Any existence of these would mean that the equation would be discontinuous. When we say hole, it typically means that it is like a circle, something like this. This one is a hole. And in this case, g of x is discontinuous simply because it has a hole. Same thing goes for jumps. J of x is an example of a function that has a jump simply because the function actually stopped at somewhere at this y value and then it jumped to another value of y here. And in that case, we cannot simply determine the exact value of our y. In h of x, we can't see any holes, gaps, or jumps. But in this case, we can see that at x equals negative a, which is the asymptote of this graph here, h of x, we can see that there will be no value for x equals negative a simply because it is the asymptote. And if x equals c, and we cannot actually find the limit at that point, then this is an infinite discontinuity, and which makes the equation not continuous. So in short, any existence of these three and the infinite discontinuity that we have as asymptotes would mean that the equation would be discontinuous. And by far, when we talk about having it in a more defined way, we could just read these conditions of discontinuity, and we will find here that the first one is that the function is not defined at x equals c. When we say that the function is not defined at x equals c, when we set, for example, a value at the domain which is c, in this case, let's just take this hole as c. So if this is c, then the function would not be defined at this certain value of domain simply because it is not included in the solution of the function itself for g of x. So that simply means that when a certain function doesn't have a solution at certain x value, then that could mean that that point is a hole. I mean, that value of x would have a hole. And having a hole would mean that the function is not continuous. The second one is that the limit of f of x does not exist at x equals c. We could simply say that this is an example, that this h of x is an example of number 2. When we say that x equals c, in this case x equals negative a, the limit of f of x will not exist in this point simply because we cannot actually find the certain value of y that would equal to negative a in this manner. And if we substitute negative a to our h of x, we could just get a value that will just increase as our x approaches to negative a. In that case, we will probably get an answer that is positive infinity, as an answer for limits is considered to be a discontinuous function. Now for the last one, the limit of f of x exists at x equals c but is not equal to f of c. In this case, when we have a function that exists at when we have a limit that exists at x equals c but it is not equal to f of c, we could simply take a look at this graph, for example, and then I have a hole somewhere here. So this is not included in the equation. But when I have something like this, which is, let's say, a certain point which is included in the equation, then we could say that this is a removable discontinuity, which I will be discussing later on. But when we take the limits as, the two-sided limit as x approaches to this value, we could say that the answer would be what the value of y here in this discontinuity. In that case, the limit of f of x exists as x approaches to c, but when we substitute f of c, this is not equal to the limit of f of x as x approaches to c. So that's how it goes for number 3. The limit of f of x exists at x equals c, but it's not equal to f of c. So all in all, there are almost like 1, 2, 3, 4, 5 kind of graphs that you would see. And this is actually what we call a gap. And there's a hole, there's a jump. This one is an infinite discontinuity, and this one is a gap. And when we talk about discontinuity, we should understand all about removable discontinuity and non-removable discontinuity. I'll be using this one. So there are general types of discontinuities, and the first one would be a removable, and the second one is a non-removable. Or we say that this is usually the infinite discontinuity. In a simpler term, removable discontinuity would mean that if we have a function f of x, and then we redefine this equation, what we will get is an equation that would have a solution at x approaches to c, or at x equals c. If we have a function f of x, and then we somehow redefine this, and even after refining we have found no solution, then this is a non-removable discontinuity. And sometimes you cannot even redefine these equations. So in those cases, when you can't redefine and you will obtain no solution for f of x as x approaches to c, then probably the answer would be non-removable. And for cases where f of x, when you redefine f of x and then you've found a solution as x approaches to c or x equals c, then we could say that that f of x is a removable. That f of x has a removable discontinuity. I think it will make more sense if we have an example, but before that, let's just proceed to infinite limits, since this is this is actually a continuation of this continuity, because it is better that we understand infinite limits before we solve problems involving continuity. And by the way, continuity is just a property of an extension of our limits that we have discussed before. It's just the behavior of the graphs that we have discussed. So when we talk about infinite limits, as what I've mentioned before about the infinite discontinuity, infinite limits are those functions that increase or decrease without bound as x approaches to c. I think I have solved something like this before. So if we take this graph f of x, and then we have a limit, we take the limit as x approaches to a positive, and we're referring to this one as our a. And when we say a positive, we're referring to all the values of a, all the values at the right of a approaching to a. So in that case, we need to find the value of y here as the limit. And as we approach to a, since this is an asymptote, it will come very close to a, but it will not touch it, and the values of y will increase in a very huge amount in this case. In that case, if I have a very large amount, a large value actually of y, then what we'll get is a positive infinity for this case. And for g of x, if we wanted to try to find as the value of the limit as x approaches to negative b for negative, so that would mean that I need to take all the values of b that is at the left. So in that case, we will consider this line going downwards and downwards until it reaches a very large value of negative y. So in this case, as x approaches to negative b from the left side, that will mean that the value would be negative infinity. So this is just what we call the infinite limits. Infinite limits are those limits that they actually have infinite values when we solve for it, and this would mean that they are discontinuous functions in which we have a non-removable discontinuity. In most cases, those are the answers. So I don't think I've written something below here, and the properties of limits, we will be discussing it along the way as we solve problems. Okay, so with that, let's head on our examples. Now let's try solving this problem. Since we've already solved some examples before, and we use that to explain the properties of limits and continuity, in this case, I'll be describing all of the solutions in a way that it will be easier to understand. And for us to understand it better, I wanted you to memorize these 3 steps that we need to remember when we are solving limits. So the first one is substitute x equals c. So we need to substitute any value of c in which our limit approaches. And then, of course, solve for it if you've substituted it. And then, if substitution doesn't work, if 1 doesn't work, redefine. So this is the second step. If substitution of x equals c doesn't work, then redefine. And then if redefining doesn't work, apply calculator technique. So this is you can't find anything like this in any website or what. But these 3 is like using a calculator technique where we find the limits of a certain function. And in this case, usually the 1, 2, 3 steps would give you almost like 80% of the problems here would give you the answers. And then the last one is which is the like one of the ultimate solution that we could get when we are solving limits that are indeterminate form, but we can't actually use it since we have not yet discussed all about differentiation. So I'll be describing all about it when we've tackled all about differentiation. And yeah, that completes the steps for our limits. And of course, we'll be having limits that you need to apply some kind of that step when we've discussed all about differentiation. So I think I'll be giving some examples for limits which we will apply step 4, of course, after the discussion of differentiation. But in this case, let's just focus on 3, and because most probably we'll be able to get all the answers by just using the first 3 steps. So remember this, you will be able to solve any kind of limit problems with these just 3 steps. Okay, so remember this: substitute x equals c. If 1 doesn't work, redefine. And then number 3, if redefine doesn't work, apply calculator technique. By the way, redefining means that you need to like apply let's say rationalizing the expression or finding its factor, then cancel it out, all things like that you've learned in high school, and probably you will be able to tackle all of them as we go on in each example. We do have a lot. Now remember this. I think I will be copying this first for our examples here. Let's just put it around here, okay? Since we're not using this space yet. So let's solve for the first one. It says here in step 1 that we substitute x equals c, and c is actually this one. Okay, so regardless of the sign, just neglect this sign, and then we'll just be using 3 here. So with that, we need to take the limit. So we substitute 3 here with x. So we have 1 over 3 minus 5 as x approaches to 3 positive. And with that, that is equal to the limit of 1 over negative 2 as x approaches to 3 positive, which is equal to the limit of negative 1/2 as x approaches to 3 positive. And remember, this rule is actually the first rule, I think. Then when we have a limit L, and we have a certain value of c here, what we'll get is simply the limit of the constant, and that is negative 1/2. So the answer here is negative 1/2. So let's proceed with the next one. We have the limit of 1 over x minus 5 as x approaches to 5 from the left. So what we will get here is simply the first rule is substitute x equals c. So that is the limit of 1 over 5 minus 5 as x approaches to 5 negative. So in this case, I will get the limit of 1 over 0 as x approaches to 5 negative. So in this case, 1 over 0, you can also apply the first rule in which the limit of a constant would be our answer, but in this case, 1 over 0 is actually undefined. So in this case, we don't allow this in mathematics, so we need to proceed to number 2. If 1 doesn't work, redefine. We need to redefine this equation. But, redefining would mean that we need to apply conjugate properties or cancel out some factors if we have. But in this case, can you cancel something out here like factors or what? You can't do anything about it since this is already in linear form. So with that, number 2 doesn't work. So we proceed with number 3, apply calculator technique. So with that, we'll be applying a calculator technique. So I think I'll just be placing something like a calculator here so that you can see what I'm doing. So basically what I will do is just use a table function, let's say f of x. Basically what I will do is use the solve function where I will be typing this 1 over x minus 5. So it simply means that I will be typing the equation, so this like your screen. So 1 over x minus 5, and then I would be substituting any value of x that is at the left of 5. That is very, very close to 5 negative. So in this case, x would be equal to 4.9999. Why? Simply because it is probably the closest to 5 that is at the left. So you can also add some 9 here and just understand what will happen. But of course, I would want you to try using also 4.99 and then 4.9 just to have some varying answers, and so that we could just get a grasp of what will happen in this equation. So with that, I'll be trying out using the solve function. So you just have to write it using the alpha x minus 5 and then press solve. Then after pressing solve, you would get something like x question mark. In this case, when you have this x question mark, it actually asks you to write the value of your x. Let's just substitute 4.9 with x, so that would be negative 10. So in this case, for 4.9 we have 10, negative 10, and then for 4.99 what we have is negative 100, and then this one for negative 4.9999. For positive 4.999. So what we have is around 1 times 10 to the negative 1 times 10 to the 6. Okay. Probably if I got the correct exponent here, then I might have gotten the incorrect. If I've gotten the incorrect exponent, then I might have used the incorrect digits of 9. But anyway, so what I'm referring or what I'm telling you about this is that when you look at the trend, you can see here that 4.9 is farther from 5 negative simply because 4.9 is not closer to 5 negative. And then the closest among these three is this 4.999 simply because it is just 0.0001 unit from 5 negative. And when you take a look at the value as x approaches to 5, meaning from 4.9 to 4.999, our value is increasing from -10, -100, and then -1 times 10 to the 6. So it simply means, by practical reasoning, that when I get closer to 5 negative from a certain value of x, that also means that I will be having a larger and larger value as I come closer to 5, meaning I would have a lot of 9999 here. So in that case, what do you think will be the answer? So of course you can use 4.887 for any decimals here. I just used 99 since it is the closest one. So your answer should be that the limit would be -infinity. So does it make sense? Because remember, as we come closer to 5 from the negative side, from the, not the negative side, but the left side, we can see that the value of y is increasing. And with that, our limit approaches to an infinite discontinuity, meaning 5 is not a solution to this equation, and it is an infinite discontinuity at x equals -5. So if I wanted to graph our function there, we could see that at x equals 5, 1, 2, 3, 4, 5, there's an asymptote here, and then this function will be it will go like this. So in this case, it would have no solution for 5, but as we come closer to 5, the value for y will just increase the negative side. That's why we will have a -infinity for this solution. Okay, so I hope I make it clear. The answer here is not 1/0, but -infinity. Okay, so if you can't find the solve function, it's just for Quotient 991ES, it's just below the shift button. So with that, let's proceed with number 3. And this number 3 is actually some kind of a function that we need to evaluate. So that is the absolute value function, and we know that the absolute value function is actually equal to -x and then of course +x. So when we substitute values that are negative and positive here, what we'll get is the absolute value. We usually use absolute value function for magnitudes or problems that we need to take just simply the value of the dimension. But in any case, we will be evaluating the limit, in which we will just take the limit of -x as x approaches to 0, and the other one is the limit of +x as x approaches to 0. In this case, we just need to substitute the value, since that is our rule number 1. So when we take the limit of 0, what we'll get is actually 0. Since this is actually -0, but you can't just take the negative of 0, that's actually equal to 0. And then this one is the limit of 0. +0 is simply 0, so what we'll get is 0. In this case, I have two values that are equal, and in this case, the limit of the absolute value of x as x approaches to 0 is equal to 0. In case where this is not the same, for example, the first one doesn't exist and this one is 0, then the limit will not exist. So let's proceed with number 4. Okay, so I hope you've already memorized this. Let's make it red. See, we're just using this general rule to solve this kind of limits. Now, here's one of the tricky parts here. The limit of a signum function x. So we first need to understand what a signum function is, and this is something like a piecewise function where we have something like f of x that is equal to x equals -1, where x is less than 0, and we also have x equals 0, and finally we have x equals 1, of course, when x equals greater than 0. So when we wanted to graph a signum function, so it's like I have a Cartesian plane here, and then we have here +1, so what we have here is like something like that, okay, and then a hole for -1, +1, and then a dot for x equals 0. So that's how it goes for our signum function, since remember, 1 here is not included in our solution, but any value that is greater than 0. So with that, let's try to analyze this function here. So what we need to do here is simply take all the limits for each case, and then we need to have an answer that is the same for everyone. So with that, let's take the limit of -1 as x approaches to 0 first. So in this case, what will be the answer? This is just another example of the basic property in which we have a constant, and of course x approaches to c. In this case, the answer is -1, since 1 is a real number. -1 is a real number. I won't box it. -1. Then we take the second one, the limit of +1, since this is x equals 1. X approaches to 0. And of course, since this is +1 and it is a real number, the answer would be 1. Now, if we take the limit of 0 as x approaches to 0, that is equal to 0. Now, let's take a look at the answers. We have -1, +1, and then 0. So, what do you think will be the limit, the two-sided limit, because this is 0, for the signum function x? And if your answer is that it does not exist, let's just write the any. If the limit does not exist, then you are correct, simply because these limits are different for each one of the equation here that we have. So it's -1, +1, and then 0. It should have been like 0, 0, 0, then we have 0, or -1, -1, -1, we have -1. But since they're all different, then the answer is incorrect. The answer is does not exist. Okay. So I hope you're not being confused with the answers here. Let's just I'll be removing the square here. So the answer for -1 is the box 1. All the boxed values or something like expressions that are boxed are the answers. Okay. So let's move on with number 5. The limit of cosecant x as x approaches to 0. So with that, that's the same thing that goes for trigonometric function. We just need to substitute. So for number 1 rule, that is cosecant of 0 as x approaches to 0. Now let's try solving for this. What is the limit of cosecant of 0? That is also equal to 1 over taking the inverse of sine. So what we get is, here is 1 over sine 0. And what do you think is the value of 1 over sine 0? Sine 0 is actually 0, and that is 1 over 0, which makes it undefined. Okay? And based on this example, since we've already substituted, 1 doesn't work, and we need to redefine. So when we redefine this, it doesn't work since we don't have a value for this one. And from this, I can actually give you the answer without doing number 3, simply because the answer here is it will not exist. Okay, so why is that? Why didn't I have to do something like substitute all the values that are near 0? So we can do that, but the thing is, knowing our function is a two-sided limit that is 0. It could have been a one-sided if it is positive or negative. Knowing that this is a two-sided limit and redefining doesn't work, usually what we'll get is an answer that a limit that will not exist. This number 2 here, I did apply a calculator technique simply because it has a one-sided limit. Of course, that doesn't work for all the limits, and for you to make sure, you need to always try it. But since by experience, I think we know that as if we have a two-sided limit where redefining doesn't work, then most of the time you will get as an answer that a limit that will not exist. But for this sake, let's try doing a calculator technique. Now we'll be using 2 values for this since we are testing our two-sided limit, since this is 0. One is as the limit of x approaches to 0 positive, and the other one is for 0 negative. For 0 positive, values that are close to 0 would be 0.00001, and then for negative would be negative 0.00001. So these are the value, and use something like a mode and then a radian. So it would be we call this your calculator won't be confused with all the values. But of course, if your calculator can evaluate in radians for these very small values, then you might as well want to use degrees or just use 0.1 or negative 0.1 in this case. So I'll just be solving it, and I'll be using 1 over sine. I'll just type in 1 over sine and then x, and then solve, press solve, and then when asked about x, I'll be writing 0.001. Okay, so what I will get for our x is 0 positive is actually for x approaching to 0 positive, that is it increases, so that would be positive infinity. And then for 0 negative, what I will get here is simply negative 0.001, and then the answer is negative infinity. So my calculator doesn't show these exact values here, the infinity and negative, positive and negative infinity. It's just that the values are getting very large, so based on number 2 that I've explained before, the answer would be infinity in those cases. So since our right and left side limit is not equal, that is, this one is positive and this one's negative infinity, then the limit will not exist. Okay, so remember those things. When you have a limit that is a two-sided, meaning it doesn't have something like an exponent, a positive negative exponent here, you have to take the positive and negative side when you do number 3. That is when you apply your calculator technique. So don't forget that, because for example, you just use this positive 0 positive, that is all the values of your function that are approaching to 0 from the right side, then you will get a positive infinity. Then most probably you'll be answering here the positive infinity, which is incorrect because the limit does not exist because x approaches to 0, which is a two-sided limit. Okay, so let's move on with number 6. So in number 6, this is actually a polynomial function, and I think this is the easiest one here. So since this is a polynomial function, so we just need to substitute the value. So that is 4 times 2 cubed minus 13 times 2 plus 1. So the limit is simply equal to 7. So the limit for this one is equal to 7. Okay. So let's move on with number 7. I think I'll be using a different color just to avoid confusion. Okay, let's just use blue. Okay, so this is a rational expression, and either way, number 1 rule states that we need to substitute c here. So what we get is the square root of 2 to the 4th plus 9 times 2 plus 1. So that is simply equal to I'm just using the calculator here, so that's why I want to use it. That is simply the square root of 35. Okay, so that's the answer for our limit. Okay, so the next one is the limit of cosine of x as x approaches to pi over 2. So we just need to substitute here pi over 2, and if you have obtained a real value number, that is cosine pi over 2, and cosine pi over 2 is 0. 0 is a real number, so in this case the answer is 0. For the next one, we have the limit of tangent of x as x approaches to pi over 2. So what we have here is just to take and substitute pi over 2. Okay, and remember, pi over 2, tangent pi over 2 is not easily evaluated by using simply tangent. We might as well, or you might want to substitute sine so that you can get an idea of what would be the answer here. So in this case, sine pi over 2 over cosine pi over 2 would mean that sine pi over 2 is 1, and then cosine pi over 2 is 0, and 1 over 0 is actually undefined. So in this case, we need to redefine this equation. But remember, this is already a basic trigonometric function where you can't do anything about it for redefining, since we cannot cancel something out here, cannot apply properties, since this is just tangent x. So what we'll do here is simply number 3 and then substitute our pi over 2 here. And remember, this is a pi over 2 negative, so that is values that are approaching to pi over 2 from the left. So from the left, that is, we can say that x is equal to, since pi over 2 is around 3.14 divided by 2, that is, we could just take the values that are really close to pi over 2. When we evaluate pi over 2 in terms of regions, this is actually equal to 1.5708. So that is the value of our pi over 2. So let's just make it something like this. Okay, it should be like 79. Let's have the most number of decimal places that I can write, so that I can actually have the same value. So x approaches to 1.570796. I did this just to have the values, just to know the values of x that I'll be using. So if pi over 2 is equal to 1.57, then in terms of region, the one that is very close to pi over 2 from the left side would be something like just 0.001 unit less than this x value. So I can just use 5706 just to make it a very close value for pi over 2. So let's just try using these values, and also something like 69 would be closer. Okay, so something like these values. Okay, so with that, I'll be using my calculator, be using tangent, so that is tangent 1.57069. I'm using in the radian mode. So the answer, as you can see, as we go on to a very, very close value for our 1.5709, what we get is a value that is increasing indefinitely. So what we have here is simply positive infinity. Okay, and just to make it clearer, remember, when we have something like a polar graph here where this is 0 and this is pi over 2, when you have an angle that is approaching to pi over 2, that is something like this, okay, then the graph of a tangent x would somehow, it will just be asymptotic to that pi over 2, so it goes something like that. And that one would simply mean that pi over 2 is an asymptote, and it increases from should be something like this. So it increases from this side, and that is simply that is simply positive infinity. Okay, now remember your tangent, also this tangent function, if you want to evaluate the value that is approaching from the positive side, we will refer to any values that are greater than pi over 2, that is greater than this 5707. We can just try 8. Pi over 2 actually would have a negative value for that, and this is actually the graph of tangent function. Remember, this is pi over 2, and it is asymptotic to y-axis, or pi over 2. From the left, it is a positive infinity, and from the right, it is negative infinity. So just additional information. So with that, let's proceed with number 10. So for number 10, the limit of this, now this one is a rational expression. First things first, let's substitute the value. So from now on, I will not be writing the limit, although that's the correct way of solving. It's just that it will make this video very long. So I'll just be substituting the values, and you will understand it, that you should have something like the limit of blah 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 x to. I will not be writing it anymore. So that is 3 times 2 minus 4 divided by 2 plus 2. And can we get a real value number here? So if yes, then that's the answer for our equation. So that is 1/2. So the answer here is simply 1/2. Now let's take a look at this second one here. If I wanted to substitute here, 3 times 2 minus 4 and then 2 minus 2. So I don't need to like evaluate this further, simply because what I will get is an over 0. And any number like here, though it is like 2, any number here will make it simply undefined because there's a 0 here. And since we do have an undefined term, and number 1 is not applicable, let's try to look if this can be redefined. Since this is already a linear, we can't do anything about it. We can't rationalize this simply because this, we cannot multiply this with the conjugate simply because we don't have any conjugate here. It doesn't have any radical sign. So what can we do, and what can we do here? So redefining is not possible. And number 3, we should be substituting values. So remember, this is we have positive and then negative here, since this is a two-sided limit. So when you substitute values that are positive and negative, then you must take the values for that. And remember, since this is a two-sided limit, as what I've mentioned before, like I think it's sine, since that one is a two-sided limit, and redefining doesn't work, so usually the answer would be the limit does not exist. And you might as well want to try. For example, I'd be using like positive here, so that is around 2.0001, and my answer would be positive here, and that is like positive infinity. And then for this one, if I have something like 1.999, then x minus 2, that value will be a negative 0.0001, and that will make it negative infinity. So positive and negative infinity makes the equation, or make the equation, the limit will not exist simply because they are not equal. Okay, so now let's try doing number 12. Why is it? It's just the same. Okay, never mind number 12. It's just the same. So let's move on with number 13. I think I have a typographical error. I don't know where. But anyway, let's just move on with this. Still have a lot. So number 13. Now let's try substituting the value. So what we get here is negative 1 squared minus 2 times negative 1 plus 3 divided by negative 1 plus 1. But remember, negative 1 plus 1 would be 0. So substitution doesn't work. Now let's try redefining. Now, can this be redefined? Remember, this is in a squared. So we might as well want to take the factors of this x squared minus 2x plus 3, and probably we might be able to cancel out. So let's try having the factors. That is x, and then this is positive 3. So of course I have 3 here, and 1. Let's just have this 1, and then 3. Since this is positive, it can be negative, 2 negatives or 2 positive. So if I try something like 2 positive here, what I will get here is x plus 1, and then the middle term would be 4x. Now if I did something like negative, what I will get here is simply negative 4x. And can I try doing something like positive here, and then I will have something like negative 3. So with that, even though with that, I can't actually factor this out into a way that I have negative 2x. So in this case, since I have something like redefining doesn't work simply because this cannot be factored out, and this is a two-sided limit, so the limit will not exist. It would have been different if this one is negative. Okay, so I hope there's a problem that would also use that, but in this case, the limit will not exist. Okay, remember that. Now let's try doing this. Number 14. It approaches from 0 negative, so that is at the left of 0. And then we have something like 3x to the 4th minus x cubed, x to the 4 plus 5x cubed. So in this case, let's try substituting. And when we substitute the value of 0, what we get is 0 over 0. Since these all have x values here, x variables here. Now this is an undefined term. We don't allow this in indeterminate form. So we don't allow this in mathematics since we don't have that kind of expression. So let's try redefining for the second one. So I can factor out x cubed from this one, so I'll be left with x plus 5. And then I can also factor out x cubed from this expression, so I will be left out with 3x minus 1. So in this case, I can now cancel out x cubed, and I'm left now with x plus 5 and then 3x minus 1. Now I can now substitute the value of 0 here, that is 0 plus 5, and that is 3 times 0 minus 1. And then I will get here 5 over negative 1, and that is equal to negative 1 over 5. So the answer here with the limit is negative 1 over 5. So what if you skip number 2? For example, you were not able to redefine this, saying that, okay, I can't redefine this, but this is a left side limit, or you wanted to like skip number 2 and then try substituting a value that is at the left of 0. So that would mean that I can substitute something like a value of negative 0.00001, something like this value, and then probably solve for this. Now let's try doing that. I wanted you to write the equation at your calculator: x to the 4th plus 5x cubed and then 3x to the 4th minus x cubed, and then try to solve and then use like something like negative 0.001. Okay, so you should be getting the same answer, which is negative 5. I'm sorry about this, negative 1 over 5. It should be negative 5. Okay, so you should also be getting the same answer, negative 5. And to tell you honestly, the third step, which is the calculator technique, it is the final step for solving almost all the limits, because most probably you will be able to get the answer by simply knowing the value of your limit here. I mean, the C value that we are approaching. If you can understand how it works for the negative and for the left and the right hand side of the limit, then you can have a perfect score for this kind of limits. Now let's try doing number 15. Okay, so in this case, I have a trinomial here and then a square. So if I wanted to like substitute 2 here, what I will get is 4 minus 6 plus 2, which makes this 0. So I'll just proceed with number 2, which is redefining, since I will get 0 at our, so it's something like value here and then 0, so we don't allow that, so let's proceed with redefining. So when we redefine, since this is in cube, so we can probably find a factor here, but since this is cube, I need to like try for all the possible values. And remember, x cubed minus 6x squared plus 11x minus 6 is actually a trinomial. And in your high school, you used to like do this by finding the factors of negative 6. That is, for example, the factors of negative 6 would be like 6, 1, 2, and 3, and all the positive negative values that are incorporated in this. And then you will do something like synthetic division, and well, that's okay. But in this subject, although you should be using that, I will be skipping those skills, since I know you have already studied about it and you should know things about it already. So let me teach you another calculator technique where we'll be using a function in your calculator, which is the equation, and then there is this number 4 here where we will be using a trinomial. You just need to write all the coefficients, that is negative 1, negative 6, 11, negative 6, and just press equals. So you will get there the value of your x's, or those are the roots of the equation. So what we'll get is x sub 1 equals 1, and then x sub 2 is equal to 3, and then x sub 3 is equal to 2. So we have 3 factors here. So with that, we can rewrite this as the limit of x minus 1 multiplied with x minus 3 and then x minus 2. And then the same thing goes for your denominator, though this can be solved easily with our techniques in quadratic equations. So we could have here x, and then we have negative here, but this is positive, so what we'll get here is simply negative for both factors. So let's check. Negative x minus 2x would be negative 3x, and this one is positive 2. So now, redefining means that we've already factored out all of this, and then we will try to cancel out terms that are alike. Of course, in the numerator and denominator. So with this, we have here something like this. So we're left now with the limit of x minus 3 as x approaches to 2. So let's try substituting the value of 2 from our x minus 3. So what we get here is 2 minus 3, and the answer would be negative 1. So the limit for this would be equal to negative 1. So remember, if you just tried to like substitute 2 and then you will get 1 over 0, and then you need to redefine. But if you something like told yourself that this is not possible to be redefined, then you probably will be answering this one as something that does not exist. But you should understand that things should be redefined first, and if it is not possible, then that's a time when it doesn't exist. In this case, if you wanted to skip number 2 and then try doing number 3, you should also be getting negative 1. You might as well wanted to try the value that is x equals around 1.999 for positive, and then for from negative, that is this should be for x to positive, you would get 2.0001, and then for x to negative, you would get 1.999. You can substitute these two values, and these two values should have the same answer that should be equal to negative 1. Okay. And of course, you won't be getting exactly negative 1. Probably you'll be getting around negative 0.999 or negative 1.001, and that's okay. Because when we talk about limits, remember, these are not the exact values, but when we talk about limits, they are the values that the functions tend to approach. Okay, so now we're done. We're now left with 9 problems left. 10, probably. Now let's try solving this sine 4x over sine 2x. Now remember, when we substitute 0 here, what we'll get is simply sine 4 times 0, which is 0, and then sine 2 times 0, 0. And what we'll get is 0 over 0, which is an indeterminate form. So let's redefine this, since this is not allowed in mathematics. So let's try redefining sine 4x. Remember, this sine 4x can be redefined as 2 sine of 2x cosine of 2x. And then we divide this by sine 2x. And remember, this factor here can be cancelled out, so we're left with 2 cosine of 2x. Now let's try substituting this. 2 cosine of 0 is actually equal to 2. So because cosine of 0 is 1, so 2 times 1 is equal to 2. So in this case, the answer is simply 2 for this number 16. Now let's try this one, 7 in the limit of sine 2x and then tangent x. Now, can we do something like redefining here? So if we wanted to substitute sine 0, and then this is actually tangent 0, what we'll get is an undefined, so this should be redefined. Now we proceed with redefining. What we get here is 2 sine x cosine of x, like what we did in the previous number. And then, since if I will be writing tangent x, we can cancel things out here, but I will be using sine x over cosine x simply because that is the equivalent of tangent x. Now remember, I can cancel this out since this is at the numerator and denominator, and then this will be multiplied at the top. So I will be left with 2 cosine squared x. And in this case, if I wanted to like substitute 0 with this equation, I will get 2 cosine squared of 0. And cosine 0 is 1. Squaring it would give me 1. And the answer here would also be equal to 2. Okay, so now we proceed with number 18. So in number 18, let's try solving it by substituting first. So what we'll get here is square root of, by substituting, we get 15 plus 4. So we have 19, then divided by square root of 0. And square root of 0 is 0. So this is not allowed in redefining. So in mathematics. So we proceed with redefining. Now, expressions like this in our rational expression where we have a radical sign, we can usually redefine this by multiplying its conjugate. So with that, let's try redefining this by multiplying with square root of minus 5. Usually, we need to redefine this by either removing the radical sign or just taking what is the conjugate of this inside. But since this is just a radical sign, we'll try to like multiply this with x minus 5 and then multiply this by square root of x minus 5. Now, in this case, even though we are able to remove the radical sign and then place it somewhere like x minus 5 here at the top, into x plus 4, and then we'll be able to remove the radical sign. When we substitute this to x approaches to 5, what we will get here is simply 5 over 5, which is 0. So this is still not allowed since you can still have a value here. That's how you redefine this rational expression with a radical. But still, even if we redefine this, we can do something about the value with having this number over 0. So in that case, the solution for this does not exist. If you wanted to like redefine this further in a way that this will be multiplied with square root of x plus 5, which will not make any sense since you will get only x squared minus 25, which is the square root of the x squared minus 25. And knowing x squared being squared with 5 in the value of c, then you will get a denominator 25 minus 25. That is still 0, so that doesn't work as well. So in that case, this does not exist. You might as well want to try using your calculator to solve it by simply substituting the value that is at the right of 5 and at the left of 5. And the answer should be different. If you get a different answer, then the answer, the limit does not exist. So now let's proceed with number 19. Now let's try doing this one. So that is x plus 3 over square root of x minus 3. Now, if we substitute a value that is 1, the restriction would be like 1 plus 3 over square root of 1 minus 3. And that is actually equal to 4 over square root of negative 2. And this makes it undefined simply because we cannot actually take the root of a certain negative value here. And even though this is square root of x minus 3, if we try to redefine this in a way that this is actually equal to square root of x minus 3, then we might as well want to try that thing just to remove the radical sign. So what we'll get here is square root of x minus 3 and then divided by multiplied with x plus 3 then divided by x minus 3. And in this case, if you want to try substitute 1 here after redefining, then what we'll get here is simply square root of 1 minus 3 and then 1 plus 3 divided by 1 minus 3. Although we solve our problem with the denominator having a negative value and then the root of that negative value, but we do have something like this at our numerator and it's still the same problem. We can't actually take the root of a negative number. So in this case, since even redefining, what we get is the same answer, which is undefined or cannot be operations cannot be continued since this is a complex. Remember, limits are only determined in a way that we're dealing with real numbers. So in this case, the limit still does not exist for this one. Okay, so now let's move on with number 20. So for number 20, what we have here is negative. The difference between these two is this one is a negative and this one is also a negative. So usually when you have something like same terms but this one is in a radical, of course when you substitute the value here, it would be 0, square root of 0, which will be undefined. So we proceed with redefining. Usually we can redefine this by simply multiplying our numerator and denominator with the expression at the denominator. So in this case, we will be able to cancel out x minus 3. So what we have here is x minus 3 square root of x minus 3 and then divided by x minus 3. In this case, we can cancel out x minus 3 and then we're left with x minus 3 square root. That means that I have square root of x minus 3, and then if we wanted to substitute the value of 3 here, what we get is 3 minus 3 square root, and that is equal to 0. So this makes sense since even though this is 0, and of course we have a root of 0, which is 0, it is at the numerator. So instead of having this undefined, because before it was in the denominator, now it's at the numerator and the answer should be 0. This behavior is somewhat exhibited something like a squeeze theorem. Remember, when we multiply certain values, then when individually square root of x 1 over square root of x minus 3 would have a discontinuity at around positive 3, but since it was squeezed by x minus 3, then the answer is 0. So that's how it happened that's what happened in this particular equation here. But you don't have to understand this squeeze theorem, sandwich theorem, do it. It's just that you just need to follow the 3 steps that we have enumerated before: substitute, redefine, and substitute. Use your calculator if it doesn't work still. Now let's try proceeding with this one. So that is x minus 2 over the square root of x minus square root of 2 as x approaches to 2. So if you take the limit of these values here, so square root of 2 minus square root of 2 would be 0. So let's now proceed with redefining. And remember, I think since number 16, we've already been redefining this equation. So as what I've mentioned before, if you remember in the video, most of the problems that you'll be solving have redefining situations. So get used to it. Anyway, so that is x minus 2. So what we get here is x minus 2 square root of x minus square root of 2, and then multiplied with the conjugate. So that is square root of x plus square root of 2. This one is square root of x plus square root of 2. So we multiplied it with the conjugate simply because we need to remove the radical sign for each term. And to do that, we need to apply this, the square of binomial, the difference of the squares of a binomial. Sum and difference, rather. So with that is x minus 2, and then multiplied with the square root of x plus square root of 2, and then divided by x minus 2. And now we can cancel out x minus 2 here. Now we have redefined the equation. We can now substitute the value of 2. Square root of 2 plus square root of 2, that is equal to square root of 4. Now, it's actually equal to 2. I'm sorry. Sorry. That is square root of 2 plus square root of 2, which makes this 2 square root of 2, okay? Sorry. Got lost in the basic math that we have. Now, what I would be telling you is that what if you've redefined this equation, something like you've already cancelled this out, and then the resulting equation would that be you can still evaluate the value of for a real number. Then of course, even though you are able to redefine the equation and the answer is still it's not still a real number, then the limit does not still exist. It doesn't still exist even though you've already redefined it. Okay, that's not a restriction even if you've redefined the equation. There are cases when you've already redefined it, you've done all the things, cancelled out some of the factors, but still you'll be able to get an undefined term, and that's okay. You just have to write the limit doesn't exist. it should likewise appear on the you're checking using your calculator for number 3 step. Okay, so I think you can see the next numbers here. So I think I'll be moving this first. So let's just move it somewhere here. 22 and 23 here, and then 24. Okay, so and then 25 is somewhere just down here. Okay, so let's proceed with number 22. So in this case, if I wanted to substitute 0 here, what we'll get here is simply 0 at the denominator, and that is not possible. So we need to redefine this by multiplying it with the conjugate of the numerator. So what we get here is square root of x, square root of 1 minus x, minus square root of 1 plus x over x, and then multiplied with square root of 1 minus x. Now in this case, this is plus square root of 1 plus x divided by square root of 1 minus x plus square root of 1 plus x. Now multiplying this respectively, what we get is simply terms that do not have the radical sign. Okay, so in this case, that is 1 minus 1 would be 0, and the negative x minus x would be equal to negative 2x. That is equal to x, and then multiplied again with square root of 1 minus x plus square root of 1 plus x. And now we can cancel out x here, so we're left with negative 2 over square root of 1 minus x, 1 plus x. And substituting 0 with that redefined equation, we're left with square root of 1 minus 0 plus square root of 1 plus 0. That is equal to negative 2 over square root of 1 plus square root of 1. And square root of 1 plus square root of 1 is simply equal to, this one is 1 plus 1, that will be equal to 2, so that is negative 2 over 2. And what will be left is negative 1. So that is our answer for x approaching to 0. Now let's move on with number 23. Now, in this problem, we have a rational expression in which it is composed of radical expressions for each term. Now, there are several approaches that we can do here. We can just first try to rationalize the expression, and then after rationalizing, of course, from the denominator, we can now multiply the conjugate. Now, for the sake of this problem, and to make this video short, I'll be doing those at the same time. Okay, so I'll be multiplying it with the conjugate and of course rationalizing this expression. So with that, we have square root of x plus 3. Let's rewrite it. Square root of x plus 3 minus square root of x negative x minus 1 divided by square root of x plus 2. Now, if I wanted to rationalize this, I can just simply multiply this with x plus 2, square root of x plus 2. And then if I wanted to do the conjugate, I'll be multiplying this with square root of x plus 3 plus square root of negative x minus 1 divided by square root of x plus 3 plus square root of negative x minus 1. Now remember, I didn't do anything about the equation. I didn't change the equation. It's just that we are redefining this. So this is just 1, this is just 1. So it's still the same equation. Now with that, I can now simply multiply all of these at once. So what I will be getting here is simply square root of x plus 2 and then multiplied with square, this one would be removed with its radical sign, so I will get x plus 3 and then x plus 3 minus negative x minus 1 divided by, that will have its radical sign removed, so x plus 2 and then multiplied with, of course, the conjugate, which is square root of x plus 3 plus square root of negative x minus 1. Okay, so that's how it goes. And you can actually do this one at a time. First you rationalize and then you do the conjugate. But since we're already here and we can just perform it all at once, and we just might as well want to explore. Okay, so with this we have square root of x plus 2 and then multiplied with this one is x plus 3 minus negative x minus 1. You can just simply do x minus negative x, that is equal to 2x. Then that is 3 minus negative 1, that is 3 plus 1, so what we have is 4. And then this one is x plus 2 multiplied with square root of x plus 3 plus square root of the negative of x minus 1. Now, as you can see here, this 2x plus 4 can be factored out. So we have 2 and then x plus 2. And then we have here square root of x plus 2 divided by x plus 2 and then square root of x plus 3 plus square root of negative x minus 1. And in this case, you can cancel out x plus 2 and you're left now with this one. So now we're finally left with this expression here, and probably we could just substitute this. So we have here the limit as x approaches to 2 negative, I think it's negative 2. Let me just, it's negative 2 from the positive side, the right side. So in this case, let's just substitute c. So we get 2 square root of 2 plus 2, and then we have square root of 2 plus 3 plus the square root of negative 2 minus 1. Okay, so in this case, I will be getting a value that is 2 and then, it should be negative, sorry. Okay, so that means this one's positive. Okay, so I'll be getting a value that is 2 multiplied with the square root of 0 divided by, this one is square root of 1, and then plus square root of 1. So what we'll get here is 0 over square root of, that is equal to 0, square root of 1. So that is 0 over 1 plus 1, and that is 2. So therefore, the answer here is 0. So in this case, the limit for number 23 is equal to 0. So we redefine it, and the answer is 0. Now, for cases like this where we can find the value for our limit by just redefining, remember, I will not allow the solution to be like, okay, use the calculator and then find the value. So I won't be using those kind of, I won't be allowing those kind of solution. Actually, number 3 is just for checking, and for those cases where redefining doesn't work. Because you have to understand that the concept of redefining is simply what we talk about continuity and limits. That is, if you're able to redefine this, for example, I have a hole here. This one hole. And then I was able to redefine it, and then there exists a solution for this one, and that's this solution. So that's how it goes for our discontinuity, but it does have a limit, like this one. The limit of f of x exists at x equals c, but it is not equal to f of c. So that's how it goes for something like this, and that's the idea of redefining. Okay, so that's all for number 23. It's quite a long solution. Nothing compared to our next topics. Anyway, so let's move on with number 24. Let's do something like 24 here and 25 here. I think 25 is an easy one. So with that, let's proceed with number 24, and this is actually a square, a quadratic function and a trinomial. Now, what we'll do here is do something like what we did before, find the factors here, and I think I can do the numerator by not using calculator. What we'll get here is simply x minus 1, and then of course it's x minus 1, just to make the middle term 2x, and this approaches to negative 1, actually positive 1. So this is actually a two-sided limit. So we have here x cubed. So I'll be using the function that is at your calculator. Let's go to 5 equation, then number 4, that is trinomial. So what we have is, here are the coefficients. So we have 1, -3, +3, and then -1. So the values of our, so the factors are, what we have here is that x sub 1 is equal to 1. Actually, x sub 1 is equal to 1. And yeah, that should be 1 and multiplicity of 3, since we do have 3 here. So yes, it makes sense, since this is 1, 3, 3, 1. How could I forget it? So that means that I have x minus 1 cubed. So in this case, I can actually cancel out 2 here, and now I'm left with 1. So I'll be solving for the limit of 1 over x minus 1 as x approaches to 1. So in this case, can we actually find a value for this if this is the limit? And that would be equal to 1 over 1 minus 1, and this is actually 1 over 0. So this term is an undefined term. So therefore, the limit does not exist, simply because we've already redefined it, and then we have two-sided limits here. So if you wanted to solve for the 1 positive and then the 1 negative, what we'll be having is the positive infinity and negative infinity, which makes the this limit which makes the limit non-existent, or it doesn't exist. Okay, so that's just for number 24. So the difference that we have here is that we did redefine the equation into a very simple term, but as you can see, we're not able to get the answer simply because the limit does not exist. And now let's proceed with the last number for our continuity. So that is the limit of x squared minus a squared as x approaches to a as x over x minus a. Now if you substitute a here to our function, we could see that we have a squared minus a squared, that is 0, then divided by 0, and that is an indeterminate form. So now we proceed with redefining. This x squared minus a squared is actually a sum and difference of x minus a, x plus a. So we can simply do this and then cancel out x minus a. So what we're left is x plus a. So that is simply the limit of x plus a. So we have now x plus a. Then if you wanted to find the limit as x approaches to a, that is simply a plus a. The answer is simply 2a. So that's how it is for number 25. So now we're done with continuity and limits. Now let's proceed with another one here from the infinite limits, and the direction is provide the vertical asymptotes. So let's go back with the infinite limits, and let's try to something like define what is a vertical asymptote. This is actually what we call the vertical asymptote, these broken lines here. And vertical asymptotes are those lines that a certain function which has an infinite discontinuity would have no solution. That means that the function would come very close to that value, but the function would tend to come closer to that value of x, but it will not touch it. So if you remember your high school days, vertical asymptotes are actually very easy to find. You just need to take the denominator of a rational expression, then equate it to 0. And remember, vertical asymptotes do not exist in polynomial function, as well as those functions that do not have a rational expression. Trigonometric functions do have some asymptotes, like tangent, but of course it doesn't obey in a way that it is an algebraic function. Remember, trigonometric functions are under the transcendental function, so they do have different tendencies. They have different ways in finding its vertical asymptotes. But anyway, we'll be focusing more on doing these algebraic expressions or rational expressions. Now let's proceed with number 1. 1 over x minus 2. Just simply take the denominator, that is x minus 2, and then equate it to 0. So what we have here is x is equal to 2. Now the vertical asymptote is simply x equals 2. That's how it goes for x minus 2. If you want to like graph it or just have a glimpse of what it looks like, if you have x equals 2 here, that is 1, 2, and this is the vertical asymptote. So this vertical asymptote, when we plot 1 over x minus 2, we can have a graph that looks like this, something like that, and then the other one I think would be something like this. Okay, so that's how it goes for x minus 2. Because as you can see here, if I have a value that is x, let's say for example I have let's say 3, so that is somewhere here, so the answer would be 1/2. And as I go on with the higher the value of x, the smaller the value I will be getting here, since x is actually at the denominator. Okay, and then as I go on a value that is near x equals 2, I will be able to get a value that is a large value for y. Okay, so now let's proceed with number 2, f of x. So that's actually y also, that is x squared minus 1. Let's make it blue. So if I wanted to like find the vertical asymptote for x minus 1, I just needed to equate to 0, and then that is simply x plus 1, x minus 1 equals 0. So I have x equals 1, x equals negative 1. So the vertical asymptotes would be x equals 1 and then x equals negative 1. So if you wanted to like graph this and then draw the asymptotes, that will be 1 here. So that is the first asymptote, and then the second one would be at the negative. So the graph should not be scaled, or this is not the exact graph, probably it will be different, but technically it would the graph could look something like this. Okay, or it could be something like this, for as long as the graph would look like something like it has two asymptotes where it will be coming close to that line, but it will never touch it. Okay, so number 3, so what we have is x cubed plus 1, that is equal to 0. So x cubed plus 1 can be written as x plus 1, and then this would be multiplied with x squared, and then that is minus x, and then we have here plus 1. So that is equal to 0. So that is equal to 0. I sounded like an Indian there. So x plus 1, x squared minus x plus 1. Now, if I wanted to ask you what is the vertical asymptote for this, we can just simply do x plus 1 equals 0, and then x is equal to negative 1. So the first vertical asymptote would be x equals negative 1. Now, how about this x squared minus x plus 1? So remember, x squared minus x plus 1 is equal to 0. You cannot factor this out. Factor this out further. And if you wanted to try to take the discriminant of this equation, what we get here is 1 minus 4 times 1 times 1. Okay, so that is simply equal to negative 3. And a discriminant having a negative value would give us a complex, or a value that is not real. So in this case, we can't have any asymptotes anymore for this factor for x squared minus x plus 1. So therefore, the vertical asymptote is simply x equals negative 1. So these are the answers for these 3 problems. Okay, now let's try solving these infinite limits. Okay, so the first one here is it's just like a review of what we've done before. So this 1 over 2 minus 2, it will make it undefined. So redefining this is not possible, and this is a two-sided limit, so the equation, the limit does not exist. Number 2, here we have Well, this is a one-sided limit, so what we have here is 3 over 2 minus 2, and having a one-sided limit, and substituting 2 positive from this, redefining is not possible, but substituting 2 positive, we will have something like 2.0001, and then substituting that from our equation, something like this, we will have here a value that is a very, very small value for our denominator, but it is a positive, so what we will get here is positive infinity. Now for number 3, this is the first time we will be solving a limit which has that approaches to an infinite number. So there are two cases here when the limit will be approaching to positive infinity and negative infinity. So the application of these infinite limits is very simple. When we're evaluating a rational expression for limits with infinity, we need to understand that we should redefine this by inspecting our denominator. So remember, the denominator only. We need to check the denominator and find the highest exponent of x. In this case, that is simply 1, since of course this is x to the 0. And having known the value of our exponent being 1, we multiply the numerator and denominator with the reciprocal of that x raised to that highest exponent. So what we mean by this is that we need to redefine this by multiplying this with 1 over x and then its highest exponent, which is 1. That is also true for the denominator. So that's it. So we have redefined this limit. And then we need to multiply this. What we get here is 1 plus 1 over x divided by 2 minus 1 over x. And in this case, we can now substitute the value of infinity. We can now substitute infinity. So what we get here is 1 over infinity and then 2 minus 1 over infinity. And now we're left with the answer, which is 1/2, simply because 1 over infinity would be 0. Because imagine if you have a very large number, infinity, let's say 99999, and then you divide it, what you have something like 1 divided by that number, what you will get is simply 0. Since of course it's approaching to a value that is 0. And it's also written here in your module, the quotient rule, that when you have a limit g of x and f of x as x approaches to c, what you will get here is simply the meaning of g of x being an L, and then f of x is the value that is infinity. So in this case, if L is any number, let's say a real number, when you divide it with infinity, the answer is 0. So that is true for this case. And number 4, so it's just the same way, but of course if you have something like this 3 to trinomial and quadratic, you can actually try to redefine this first by trying to factor out if there is a factor. But I don't think there is, since this is already x squared minus x plus 1, which is not factorable, so we can't do anything about it. So we just need to substitute infinity with the redefined equation by using the inspection of denominator. If we take the denominator here, we could see that the highest exponent is 2. So we need to divide each the denominator and the numerator by x squared. So in this case, I'll be multiplying it with 1 over x squared, and then the same goes for the denominator. So now I'm left with 1 over x minus 2 plus 1 over x plus 1 over x squared divided by, this one will be 1 minus 1 over x plus 1 over x squared. Now let's try substituting x approaching to negative infinity. So in this case, this one will be negative infinity minus 2, and then this one will be plus 1 over infinity, and this one is also plus 1 over infinity, negative, so that makes it 0. And of course 0 for the last term. And then this one will be 1 minus, of course, 0 plus 0. So what we get here is simply negative infinity minus 2. Okay, so can you subtract infinity, negative infinity, and then minus 2? So the thing is, the answer here is of course negative infinity. Why? Simply because if you have a very large number, say negative 99999, and then you subtract 2 from that value, then you will still get the same, a very large number. So the answer is negative infinity. And that property is also included in your module. It says here that if you have an algebraic operation of f of x plus minus g of x, that is equal to infinity. But I have to specify here that when we talk about negative infinity, for example, negative infinity, this is only true if negative infinity would be subtracted to a certain value, a real number, g of x. That is also equal to negative infinity. This doesn't work if we have negative infinity plus g of x, knowing that g is a positive number here. Let's say this is a positive. So the limit would not exist for this case, simply because you might be wondering, what if, okay, if g of x is equal to like 4, 5, 6, this is still true if you would still think that negative infinity is a very large number. That is true for 4, 5, 6. But what if we've set a value for negative infinity, though it doesn't have any value, but what if we set a certain arbitrary constant for negative infinity? Let's say negative 9999, just for this 5 nines. And what if g of x is equal to like positive, let's say 100,000. So in this case, 100,000 is greater than negative 99999. And that makes this not true for the case when negative infinity plus minus g of x is equal to negative infinity. So you have to be careful with those expressions where it doesn't exist. We call this the indeterminate form. So this is only true if infinity plus g of x, knowing that g of x is positive, that is equal to infinity. Now, if you have negative infinity, that is true if this is negative g of x, that is equal to negative infinity. Okay? So I hope I make it clear for those cases. So now let's move on with the last number, which is number 5 for our infinite limits. So number 5 here, we have square root of x squared plus 1 and then 2x plus 1. Now, can we try, if we try to redefine this, we cannot actually redefine simply because this is already square plus 1 and it is already at the numerator, so rationalizing it would be meaningless. Now let's try redefining this by having the exponent x, which is at this expression here. But remember, we'll only be looking at the denominator, and here it is x, so we can just simply multiply it. But if we multiply this x squared plus 1 with 1 over x, we cannot actually determine the value by just simply doing something like this, since as you can see here, we can just simply multiply this because this is in a radical form. Now what we'll be doing is simply rearranging this expression so that we can actually multiply it with square root of x squared plus 1. That is simply having this inside the radical sign, but having the square of this expression. So with that, I can have square root of x squared plus 1 multiplied with square root of 1 over x squared divided by 2x plus 1 and then multiplied with 1 over x. So this is equal, remember, if we take the square root of this one, I'll just have 1 over x, which is also equal to 1 over x. I can cancel this out and I have already the original equation. And with this, I can now proceed with the calculations. So x squared over 1 over x squared would be 1. That would be plus 1 over x squared. And that is also inside a radical sign. And now we proceed with the denominator. What we have here is positive 2 and then plus 1 over x. Now I can now substitute for the limit as x approaches to infinity. So with that, I have the square root of 1 plus 0, that is for this one, and then 2 plus 1 over 0, that is 1 over infinity, that is 0. So in this case, the limit would be square root of 1 over 2, and that is equal to 1/2. So the limit as x approaches to infinity for this case is 1/2. Now there's a trick here. If you wanted to find the limit of a function that is approaching infinity, so all we need to do is to inspect the exponent of our numerator and denominator. So if we wanted to solve immediately for the limit of this number 3, we just need to take the highest exponent for our numerator and then the denominator. In this case, the highest exponent of our numerator is 1 for x. So for x, for our numerator, for our numerator that is 1, and that is for x, you need to take the coefficient of that highest exponent for our numerator that is simply 1. And then for the denominator, you also need to inspect for the highest exponent of x, and in this case, it is also 1, and then take the coefficient of that exponent. So in that case, or that variable, in that case, the coefficient of the highest variable with exponent is 2. And then you just have to divide this, and you will get the same answer. That's 1/2. Okay? So let's proceed with number 4. So for number 4, if you would take a look at the numerator, what we will get here is that the highest exponent is 3. And of course, for the denominator, we have 2. When we have functions in which the numerator, when we say that the numerator exponent is greater than the denominator, exponent, of course, I'm talking about the exponent. Ito yung highest. If the numerator has the higher exponent for the variable, then what you will get is simply the answer to where the x approaching to that certain limit or value. And in this case, since this is negative infinity, our answer should be negative infinity. Okay? And for number 5, let's take a look at number 5. Now, we need to take a look at the highest exponent of our numerator. That is squared. I mean x squared. But of course, if we would just say that this is 2, it would be wrong simply because this is included in a radical sign. And if it makes sense that if we add something like a radical sign here, what we'll get is simply x. And in that case, the exponent for our numerator is 1. Okay? So remember that it should be something like you need to account the radical sign here, and for example, if you have, let's say, x cubed and then you have something like radical sign here, then the exponent should be around 3/2. And in this case, it is 1 since I already have 2 here, a radical sign that is square root. In this case, for our numerator, that is 1. And how about for our denominator? That is also 1, and then for this case, we have a coefficient that is 2. Since we do have the same exponent for this one, and then the numerator have a coefficient that is 1, then we just need to take the ratio of this and then just do something like a fraction line, and that should be the answer for our shortcut method. That is 1/2. Okay? So I hope I wasn't too fast for such. For example, I wanted to like find the limit as x approaches to, let's say, positive infinity, and then I want you to like find the something like this, and then we have, so you can do the things that we did before, the long method in which we need to find the highest coefficient, the highest exponent of our x here, which is 3, and then divide both sides with it. Okay, so we can do something like that and then substitute the infinities. Now, in this case, I will be doing the shortcut method, and I will just be finding out the highest exponent of our numerator. In this case, it's 3. And for the denominator, it is 3. Since, let's say this is n, we call this n, the exponent for our numerator, and this one is m. Since n is equal to m, then we just need to take the ratio of our numerator and denominator's coefficient for that highest exponent. In this case, that is 4/8. So therefore, the answer for this is 1/2. You can also try doing the long method and you should be getting the same answer. Let's do something like this one. The limit of, and let's say we have 5x squared minus 7x plus 1, then divided by x minus 8 as x approaches to, again, positive infinity. So in this case, if we were to take a look at this one, we have square here, and this denominator does only have 1. So since n is greater than m, meaning 2 is greater than 1, what we have here is the limit of our x would be positive infinity, meaning any value na our x is approaching. Okay? And the last case is when the limit, for example, we have x minus 4, and then we have x approaching to negative infinity, we have x to the fifth minus 7. So in this case, what is the answer using our shortcut method here? If in this case n is less than m, meaning the numerator's exponent highest, which is 1, is less than m. If we add something like x squared here, it is still lower since 2 here is less than 5. So in this case, the limit of, or the answer here would be equal to 0. So remember those 3 cases where we have equal, we have the ratio, which is numerator denominator, we have here the infinity, and then 0. So to prove that, let's just solve this expression using our conventional method of solving infinite limits. So remember, I told you that we just need to take the reciprocal of the highest exponent in the denominator, that is 1 over x to the fifth. Then multiplied it with 1 over x to the fifth as well. And then what we'll get here is 1 over x to the fourth minus 4 over x to the fifth plus 1 over x cubed. And then this one be divided by 1 minus 1, 7, 1 minus 7 over x to the fifth. And in this case, if we substitute, we take the limit as x approaches to negative infinity, what we'll get here is 1 over infinity minus 4 over infinity plus 1 over infinity. Well, let's just make it 0. Since we just substitute the values here, and then we'll get 0, and then 0, and then 0, and divided by 1 minus 0. So now, finally, we'll get here 0 over 1, which is also equal to 0. So that makes sense for our answer here for the long method. So remember, the shortcut here for the limits or infinite limits is something like this. Or remember also that it is only applicable when x approaches to a certain infinite limit here, but infinite number, okay? But if it is not something like that, for example, this one, it's a real number, so it's not applicable, okay? So don't forget it. And since we already discussed all of the limits and continuity and all of the cases where we have infinite limits, we'll now be proceeding with differentiation on our next video tutorial. Okay, I hope you've understood this with the many examples that I've given you. And if you still have further questions and some solutions here that is different from you, probably I just miscalculated somewhere, then we might also want to talk about it. Just message me or use the Google Sheet if you want to ask something. Okay, so thank you and see you next time.